Hello everyone. I will introduce today our guest, Matthias Halisch. Matthias is a senior research scientist from Leibniz Institute for Applied Geophysics from the Department of Petrophysics and Borehole Geophysics, Hanover, Germany. Matthias completed his PhD at Technical University of Berlin, the Department of Geophysics. His research interests are petrophysics, where currently Matthias focuses on complex electrical properties, X-ray computed tomography, he works currently on Pore and grain geometry topology, and digital rock physics, concentrating on two-phase flow and NMR simulations. Matthias has 29 articles and 25 articles in the Society of Core Analysts, 25 papers of the Society of Core Analysts, and he will explain what it is. Matthias was awarded by numerous awards like Young Professional Award of Martini Foundation and Society of Core Analyst Award. Please, Matthias.
Yes, Regina, thanks a lot. In advance, my apologies if my voice sounds a little silly. So obviously the weather in Germany is quite different than here. We have about 0 degrees C, and here we have about roughly 20. So I'm suffering from my cold, so my apologies if I sound a little bit silly or need to drink a little bit water. Gina, also thank you for the kind invitation to come here and to present a little bit what we're doing in Germany. Before I start, I will give you a short introduction about our institution, just from a nutshell what we're doing, so that you're all aware of how we are organized and what we are working on. As Regina said, that's the name of our institute, the Leibniz Institute for Applied Geophysics. In Germany, you have 4 major research foundations. Maybe you have heard about them. Helmholtz, Max Planck, Fraunhofer, and Leibniz is the 4th one. Yeah, in Leibniz, you have more or less the applied working institutions in this area. We're located in Hanover, in the center northern part of Germany, and we are forming with 2 different institutions this so-called GeoCenter Hanover. At the same spot, there's located the State Authority for Geology and Mining of Germany, as well as the National Authority for Mining of the state of Lower Saxony, where I belong from. And of course, this institute as a third-party institute. In total, in this GeoCenter, we are about 1,100 employees working on geoscience and geoscientific questions. The LIAC itself has roughly 110 employees, mainly focusing upon geophysical applications. The institute is divided into 5 different departments. So Department 1 is seismics, gravimetry, and magnetics. Department 2 is electromagnetics and geoelectric. Department 3 is a little bit special. That's about geochronology, because we have a lot of research questions concerning paleoclimatic questions at this point. So we need some methods for dating the material and so on. The department number 4 is specialized in geothermics and information systems. And the department 5, where I'm from, is focusing upon petrophysics and borehole geophysics. Yeah? I'm in charge of the petrophysics laboratory, and what we're doing, we're making more or less the entire range of petrophysical applications, from standard core analysis to special core analysis. And we have 3 main research foci. One is, of course, complex electrical properties on a broad range, nuclear magnetic resonance as a 3rd one, and then in combination with the high-resolution imaging techniques, because most of these methods are aiming for the interface between your mineral surface area and your pore fluid or anything else. So the interface between these different phases in your system is of interest, and that's why we're organized in this way. So today's talk, I will introduce you a little bit about and tell you something about enhanced pore space characterization by means of MicroCT imaging, so high-resolution imaging and spectral induced polarization as a very commonly used laboratory technique in petrophysical applications in Germany. And I divided it also in two parts, so also want to stress my co-workers and lots of cooperations here, also international cooperations that our institute is focusing on. So part one, the MicroCT imaging. Probably a lot of you might have heard anything about MicroCT, or you have been to the hospital where you have in the need of a medical CT. The outline of this first part, I promised Regina not to show any formulas or algorithms or anything like that. So I'm just showing in general how it works, what's the method all about, and what are the clues for using these methods. Yeah, so I will give you the take-home messages when we reach them. Yeah, that are the things that you should remember if you're ever going to work with these methods in your career. Nevertheless, I have one simple formula for if we go to the complex electrical properties. So I will start off with the basics of MicroCT imaging, a typical MicroCT workflow, typical processing errors that you can see or that you can easily happen during your process. Then something about the determination of Pore, in brackets scale geometries. We apply this mostly on the Pore system. Yeah, the workflow is the same if you apply this to the grain system, to the matrix, to the minerals, to anything else we want to see in this. We're focusing on the Pore system here. Some conclusions, and then we'll switch to part two, the SIP as it is abbreviated. So, MicroCT imaging in a nutshell. So a laboratory CT looks like this. So a little bit different than a medical CT. Here we have a fixed tube. That's like this. That's our X-ray source. We have different geometries of beams that can come out of this tube. In this case here, it's a cone beam. We have our sample that needs to be investigated. And here's the biggest difference to the medical CT. In this bench-type CT systems, the sample itself rotates. In a medical CT, the source and the detector system will rotate around you. That's why it's so loud, and that's why you got to be into this tube. I think you agree it would be inappropriate to rotate the patient inside of the tube. Yeah, so that's the biggest difference. And here we have a classical detector. So that's a 2D detector. They have a huge variety of pixel pitches and pixel sizes and resolutions. In this case, this is the device I will point out a little bit later. We have a 5 megapixel CCD detector. They have a huge variety of acquisition times. So you can go from long acquisition times for straightforward imaging only to very short acquisition times where you can also perform 4D experiments at this point. Yeah. So, but here for the classical CT, we're down to the long acquisition time. So the basic principle for every CT is just the same. You have your object of interest, and then you scan it and you perform your data acquisition. How does it work? You have a cone beam or anything else from your X-rays, and you take a collection of projections, two-dimensional projections from your image. These projections, you can stack them, and then you need to process them in advance to make the 3D model out of it. And typically, by some black box algorithms, these projections are somehow weighted and filtered. They need to be weighted. If you think about a cylindrical sample, the pathway from the X-ray through the sample is in the middle of the axis of the sample, the longest. And on the outside of the cylinder, it's the shortest pathway through the sample. That means that on your detector, the energy from the shortest pathway that gets to the detector is higher than in the center of your sample because more X-rays have been absorbed because there's more material. Yeah, and this needs to be weighted so that you have a smooth and plain projection that you can reconstruct, actually. You can apply some filters. I can say from experience, this is a bad thing to do because you disturb your image already at this point. So if you can avoid it, don't filter your projections here at this point. Many systems do not allow to manipulate this workflow. Yeah, so if you want to buy a system or you have a system, always ask the company what's going on here at this point. Yeah? Otherwise, you don't have control about your results. Then you can perform the back projection process, where this two-dimensional filtered and weighted projections are projected back into the source point, and then you got your reconstructed object, and you can visualize it in a different kind of way. One thing you need to be aware of is that this is only an approximation of your original object, and it's highly depending upon the resolution that you're able to achieve. It's only, this result here is only valid in the boundaries of the resolution of your scan. Anything you cannot see or you cannot resolve is out of interest and out of focus of investigation at this point. So the system that we're using in Hanover is a GE Phoenix X-ray nanotome system. It has a tube characteristic like this, so maximum tube voltage or acceleration voltage is 180 kV. Maximum target power is about 15 watt, which is sufficient enough to go through samples, that are of this size in maximum. So that's what you can easily achieve with this rocks. If we're talking about high resolution imaging, we're talking also about smaller samples. So you cannot resolve high resolution with a classical CT with large samples, so you need to downscale your sample size a lot. This is an inherent protected device by law, so you can see there's a lot of shielding material here. It's quite heavy, it's 1.5 tons. And if we look into the inside, this here is the Xray Tube. It's a water-cooled tube with a tungsten target and a germanium window where the X-rays are transmitted through this. This here is the rotation stage where the samples are placed on. This is an air-beared rotation stage you can find in any kind of CNC machine or drilling device. And you have the detector here on the left-hand side. Something special about this device is that you can virtually extend the detector plane along the x-axis. So you can skip this 3 times so that you're able to also scan very broad samples in the full field of view. So that's something special. Of course, this means that you double or you triple your acquisition time. So it always comes with a drawback. The clue about this device is that in order to get sharp images, you need to have an X-ray source or an X-ray tube that is able to produce very narrow focal spot points. The smaller the focal spot point of your X-ray tube, the sharper your image will get due to this so-called Penumbra Effect. So if you have a focal spot with a few micrometers of diameter, so you're going away from an ideal point source, you can see here by just painting the pathways of the X-rays from each point of this focal spot, you can see that you got a blurred image of your object. And that's really an issue for many systems that you need to be aware of. So if you see images that are really blurred or unsharp, this might be an issue here that you have a focal spot size that is bigger than the geometrical voxel resolution you have been able to detect to achieve. So as a rule of thumb, and what you should remember of is that the focal spot size dominates the image sharpness and the detail detectability. So the smallest feature that you're able to detect in your image is about 1/3 of the size of the focal spot. That does not mean that you are quantitatively able to extract this information, just qualitatively to detect it visually in your data. And for this device, it means we have a focal spot size in range of 600 nanometers at best. So the smallest feature that we're able to detect qualitatively is in range of 200, 250 nanometers at this point. Typically, for small samples, the resolution is in range of 1 micron. True spatial resolution that we're able to achieve. So in the typical workflow is something like this. You have a reconstruction pattern as seen. State of the art is, of course, GPU based. Otherwise, you would reconstruct forever. 1 cubic millimeter of rock sample on a CPU based cluster would take about 10 to 12 hours reconstruction on a 1,000 cube volume. So on a GPU based, you're down to minutes at this point. So you're not limited through this narrow gap here anymore. Then you perform your 3D data processing with any kind of special software. So the most common one for image analysis is Aviso. Maybe you've heard about it. Then, of course, you go into detail, and the typical thing afterwards is there you perform some filter operations, and then you characterize your mineral phase or your pore space and so on, and you perform some kind of segmentation by different types of workflows that you're able to achieve. And I said, here, things can get horribly, horribly wrong, because the processing and the manipulation of the images directly influences any results that you're able to get out of it, either qualitatively or quantitatively. And just to highlight this, some effects of filtering or false filtering at this point. So this here is a young tertiary sandstone from the USA. This is the raw image as it gets out of the device. Yeah, this is the quality that we're able to achieve. It's not too bad. You could already start working with this if you would like to. In many papers, you're able to read, yeah, then we performed some filtering, and the resulting image looks like this. So the question is up to you. Is this an advancement contrary to this, or is this worse than this? I would say it is worse. The image is more or less completely blurred. On the first picture, it seems to be of higher quality in terms of noise inside of your grains that you're able to see. But if you look at the edges, you can see that information is lost due to the filtering process. Yeah? So if you perform a correct filtering operation, and it will take some time to get the correct filter algorithm setups and so on, and you should take this time, you end up with images like this. Yeah? So you got reduced noise inside of your grains and still have sharp image boundaries or grain boundaries at this point. So we can skip back again, just so that you're able to see the difference. Especially here in this mica, you can see the difference between the filtering operations. So this was the first point where you can start to mess up with your data. The second thing is, of course, if you zoom in and you want to distinguish between the material and the pores, yeah, what's material and what is pore? Yeah, so if you zoom in and you see here the single voxels, and these small bricks here have an edge length of 1 micron. So where would you draw the line? So where would you estimate what is matrix or mineral phase and what is pores phase at this point? And of course, you manipulate this boundary here already by the filtering process. And that was what I wanted to show you before. If you blur this, this information is lost on a small scale. So if you want to resolve the small features, and they are not so really small, you can see here, we have here roughly 20 microns in diameter for this one here. You need to know what you're doing at this point. So in the end, you might end up with something like this. Yeah, you make your segmentation, and then you got your filled up pores at this point here. And from this, of course, this here is not the true topology of your material. If you're talking about MicroCT or any kind of imaging, we're always talking about this Lego brick-like surfaces. If you extract this information, the surface is smooth, and there you can manipulate the structure again by telling how rigorous or how restrictive this filter operation and the smoothing operation should work on your topology. Yeah? And again, if you want to resolve small features, you need to try and cross-check every time you're doing this operation. So also very time-consuming at this point, and it really comes down to experience of the analyst. So what you end up with, I think this is a little bit blurred as well. So from your 3D image here, you get this distribution of gray values throughout this volume. So every gray value stands for distinct phase information inside of your material. In an easy case, I hope we can see this, we have this bumps here, so this maximum and this maximum. The gradient is a little bit more distinct here, the red one, the red line. That's the separation between the air in the system, so the pores, and the minerals that come afterwards. So all the grains you can see here are on the right-hand side. On a medical CT, you're a little bit limited if you want to evaluate the mineral composition of this material, because normally medical CT work with a 12-bit reconstructed volume. That means gray values from 0 to 254. That's what you're able to put into a 12-bit system. So that's insufficient for quantitative analysis of the mineralogy of your system, because the mineral phases exist in arbitrary complexity and phase accumulations at this point. You have alterated mineral phases, partially transformed mineral phases, and you try to compress this information in a 12-bit system. So every mineral phase, in the best case, would be in one bin on your 255 gray values that you're able to have. If you go to a 16-bit reconstruction, as we do, you have 64,000 gray values as placeholder for your information inside of your sample. And as you can see, so this here behind is not only noise, this here is also high absorbing mineral phases like zirconia and anything else, or hematites and this stuff. There's still mineral phase information inside here, and we almost need the entire range of gray values. Yeah, so that's very important. And of course, if you miss this point here where you make your segmentation work, just as an information, you manipulate the pore system and the volume that you derive out of it. Yeah, so, and some rocks are very thankful for this operation, so nothing big will happen and nothing bad will happen to your data. Others, this is the relative change of the porosity by segmentation threshold errors. Even small changes in the segmentation threshold here, in terms of less than 1% absolute threshold deviation, will change in more than 10% volume difference inside of your system. Yeah? So the takeaway message is segmentation is not easy and needs a lot of cross-checking with the material that you're doing. And if you've done this, this is the typical image that you get. You have segmented your faces, and then of course, which is really nice, you're able to extract these faces really easy. So this here is a sandstone, grayish is the matrix, and here in this yellow color is the pore system. So you can disconnect both from each other, and then you can work on the matrix and the mineral phases and on the pore system as well. As I said, we're concentrating here on the pore system. And of course, if we have the entire pore system, we have the porosity of the pore system as a function of the image resolution. Yeah? So of course, we're not able to detect the entire porosity that we're able to measure in the laboratory, yeah? Because we have the resolution threshold that pushes against this. So we're not able to detect small pores. If we cannot detect them, we cannot quantify them. And that's why a CT porosity is always underestimated against the laboratory porosity at this point. If you see something different, you should say, stop, maybe it's not representative anymore. If you have a representative volume, you should always be lower than your laboratory volume. But now we're interested in individual pores. So how do we get individual pores or individual grains or individual structures out of this information? One way to do this is to apply so-called watershed algorithms. You can easily make some Google research or anything else how this works. So just as a nutshell, the structure you're interested in, you can imagine this as a connection of valleys and of hills if you make the gradient mask of your image. And then nothing else has happened as that you are filling up these valleys numerically with this gray values here. And as soon as here the maximum between these valleys is reached, there you can set, okay, this here is my watershed. Here I have 2 individual structures or even 3 individual structures that are connected, but they need to be treated as individual structures and not as one structure anymore. So you can get from this connected image to this disconnected image here. And that's exactly what we're doing. And of course, again, you can mess around. You can say the algorithms and typically how rigorous or how restrictive they should work. And if you say, I don't care at all, nothing will be separated. That's the easy case. Or you can see here some pores are still connected to a large extent and only a few are disconnected and so on. So again, this continues here. You need to find the best fit parameters for your algorithms. And this needs to be done manually. Well, the watershed works that you give some kind of weighing factor, how big the relative difference between this maxima should be, where it should be able to detect. And if you say, yeah, okay, I have a small weighing factor, then this probably would be only detected as one system, like on this case here. If you say, yeah, I want to have a really high weighing factor, so more or less every single method or value should be separated, then you end up with something like this. This might also happen that you can over-segment your pore system. Yeah. In our institute, in our department, we're taking lots of efforts in cross-checking with other analysis techniques. So with the 2D impressions from the images as well as from SEM images we have, and we are able to register with this 3D volume. So in practice, we have our samples, we scan them, we make our analysis, we cut them apart, we polish, we make a thin section and SEM, and this image can be registered into the 3D volume. So we are able in different actual directions to distinguish, is this the best fit segmentation and separation of pores. You will never have a perfect separation of pores at this point because the algorithms are still too stupid at this moment. Yeah. It's always a compromise.
Do you work on the watershed works on the intensity of the picture? Or
Yes. Just a note, we want to overcome this issue here because watersheds are still a little bit, yeah, they're commonly used, they're easy to use, but you need to know what you're doing, and the post-processing is really extensive. We want to...
But there is not a straight physical distinction between the intensity of the image and the grain itself. So
Yeah.
it's very tricky.
Yeah, it's tricky. There are some approaches by some machine learning algorithms to detect the shapes and therefore individual pores. So that's an actual project that we're applying for funding at the moment to apply machine learning networks at this one, because we think it's more promising for the segmentation and to prevent the over-segmentation of the pore system. So we now got individual pores. So how can we characterize these pores more in detail? Yeah. So the question is, how can we estimate the geometry of this pore? And I got just segmented here one pore for you. So what's the shape or the geometry of this pore? Yeah. Again, you can only make a rough estimate about this geometry. The easiest one that you're able to do is you put a surrounding bounding box around this pore, and then you got your descriptors in X, Y, and Z direction. That's straightforward. That's commonly done. But you can also see what happens. So is this here the true length of the pore? As you can see, the pore is a little bit shifted in this direction. Yeah. So the true length of the pore would be something like this and not like this. Yeah. So it gets tricky again at this point. Then you can apply some advanced methods again, so ferrite caliper analysis and so on, where you use dynamic flipping bounding boxes and parallel sheets, and they fit the geometry better than this conventional bounding box methods here. But still you can see, yeah, the true length, it's not really the true length. And of course the pore entries here are highly overestimated in terms of their diameter and in terms of the true diameter. And you will not overcome this issue unless you connect this with other methods that you're able. And what's really common and comes from pore network modeling about 15 years ago is the equivalent diameter, either by maximum inscribed spheres or circumscribed spheres that you can apply to this. So you segment your pore, and then you say, so what is the diameter of the maximal sphere that I'm able to place in my pore? It gets the average diameter quite well from your pore system, but length and width is completely lost. Yeah. So as you can see, you have a bunch of parameters, and what's the truth? Yeah. So these parameters can differ significantly, as I said here. So 170 microns for the classical bounding box. It's up to 326 microns if you use ferric caliper. Of course, if we're looking only at the equivalent diameter, we are down to 117. So what is the parameter that we're going to use? And to be honest, this is still an ongoing discussion. What we use at the moment is a mixture of ferric caliper and equivalent diameter. So we totally skipped out of this one here. So you can make a more characterization and a better classification if you have these three lengths here. So the length, the width, and the thickness of your pore in 3D. And there are some schemes where you can sort this by shapes inside of it, or by a so-called equivalency plot, where you can distinguish, do I have a very homogeneous distributed pore system or a very anisotropic inhomogeneous pore system at this point. And it works quite reasonable for many reservoir rocks at this point. And of course, you're able to distinguish if I have a pore system with more cube or spherical-like pores, or have a plate-like or rod-like pores at this point. So that works quite well from experience, and you're able to make a rough classification. Again, the machine learning project I told you will try to add significantly more shapes and more differences here at this point. Some geometries from 3 reservoir sandstones from Germany, Bentheimer type sandstone, all Cretaceous except this one here. This is Middle Permian. This is the Obernkirchen. They are more like Berea type sandstones, and the Flechtingen sandstone from Permian age is a little bit different. We have Barrett cementation here and lots of hematite in it, and the pore system is also dominated by microfractures at this point. Again, you can detect your total porosity. You can detect your main pore networks. They do not necessarily need to be interconnected in terms of resolution, as you can see here. And then you can also see the remaining, so the not connected pores in this system, what we call pore ganglia at this point. And they can make some numbers, not in volumes, but in absolute numbers. You can easily get systems here with 1 million, 2 million, 3 million pores in your cubes. And if you have this information and you've segmented your pores, you're able to calculate the pore size distributions or pore volume distributions out of it. And depending on which descriptor you use, so the bounding box, the ferrite caliper, or the equivalent diameter, you get significantly different shapes of your pore size distributions that you get here. Yeah, which is, of course, again the question, so yeah, which one should I use at this point? Yeah. So, as I said, you can forget this one, and you can also forget the equivalent diameter only. This one fits at best if it comes down to pore size or pore length distributions if you decompose the ferrite caliper into X, Y, and Z component. Yeah. And then you can see, okay, so the 3 sandstone types that we have here differ to some extent. In other methods, they look more or less the same always. And then if you apply this to this classification pattern, as I said before, just here exemplary, you have your pore system. You can characterize this by shape classes. And again, it strongly depends on which descriptors you use, where you end up in your shape class and in your pore shape classification scheme. Yeah? So if you use a bounding box method, you will end up here. So yeah, more or less equant pores. If you use a ferrite caliper method or something else, you can clearly see that there's a shift towards other shape classes that you can detect in your system. This, of course, would severely affect your characterization of your pore system if you rely on this data only. It gets even worse if you have more complex systems where you have issues with segmenting these pores, where you not only have a shift into this direction, but also here to the upper left corner, yeah, which means a completely different classification scheme for your rock types. Last but not least, so this here is just also the effect on the total volume of pores detected for each method on different volumes that you're able to detect in your system. Of course, the amount of pores that you're able to detect depends on your volume that you investigated here at this point. If you have very homogeneous rock types, small volumes are sufficient. If you have inhomogeneous ones, you need larger volumes to evaluate. And it can take some time to calculate all of this one here. Again, if you are looking only at equivalent diameter, so you will end up still with something cuboid or sphere-like. That's just in the method how it works. Yeah. So the other schemes are probably better to distinguish between different shape classes here. Okay, so conclusions for part 1. I'm now working here in this field for roughly 15 years in the CT imaging community, and it is a very powerful tool. It's three-dimensional. It's non-destructive to your material. Yeah? You can make qualitative and quantitative sample analysis, quite straightforward. And you have a full 3D characterization of pore scale structures and all of the processes that are going on. But you need to be honest, and you need to say it's not an easy method. Especially the image analysis is not easy to do. It's very cost and time consuming if you're talking about image analysis. I have data. I measured these rock types 10 years ago, and I'm still working on the image analysis because they are advancing. You got better results, and so on and so on. So this you could take forever. The software tools to do this reliably are very cost expensive. The companies know that this is a market where they can make a fortune out of it. Yeah. So open source software is available, but only to a limited extent. If you want more, you need to program this by yourself by using MATLAB code or anything else. It's doable, but it takes time. And the results highly depend upon the processing workflow and the processing quality. That was one thing I really wanted to show you. Yeah, so your results are only as good as the process you did before at this point. So from the direct image now to part 2, spectral induced polarization. In our department, we always try to link the CT or the imaging method to the classical petrophysical investigation and method. Why? Because on the lab scale, the petrophysical method will always provide us a data set as an integrated data set of our investigated sample volume. Yeah, so we cannot tell which feature inside of this sample causes which contribution to this information and to this signal. And that's why we always try to make the imaging in addition, so that we know which controls this petrophysical parameter and where does this part of the signal come from. And I think this is a quite nice example to show how this can be combined. For this project, we have been working extensively on the so-called Fontainebleau Sandstone. So you see a pattern emerging. Mostly we're working on sandstones here. The Fontainebleau Sandstone is quite young sandstone. It's located in the Paris Basin. So here you have France. Here you have Paris. It's more or less from this region here. It's one of the largest basins of the world, formed at Permo-Triassic times, and has more than 3 kilometers of sedimentary rocks as overlaying there. The Fontainebleau Formation itself is not that impressive. It's only roughly 40 to 50 meters in total thickness, and it has been composed in 2 different environmental setups, so which is divided into a first sequence, the older one here, and the second sequence, the younger one. So on the very top, we have this lacustrine carbonate deposits that build the roof of the Fontainebleau Formation. Then we have here the upper part, the first 10 meters, which is probably a continental deposit, an Aeolian depository environment. And then we have the lower part, which is supposed to be a marine deposit environment. Yeah, so shoreline beach deposits. That's what we're talking about here. The Fontainebleau was in the past of very interest. I don't know if anybody has been to Paris. And you see the cathedral and so on. So they are constructed from this rock. and they are constructed from this highly pure parts of the Fontainebleau Formation, because the Fontainebleau Sandstone itself is almost white, because it consists about 99.9% of silica, nothing else. Yeah, so that's the speciality, and that's why in the medieval age the constructors got this. Unfortunately, if you want to investigate these rocks, you're not able to get them anymore, yeah, because this formation and the outcrops where this formation originates from are now UN cultural heritage. So you're not able to get there to probe anymore. So everything that you're able to get in these days is from the upper part or from the very lower part, which are not under this heritage. But there you have the problem, they are not pure anymore. Here you have some quartzitic deposits on the upper part. In the lower part you have some severely volume amounts of clay inside of your sample. Yeah, so that's a significantly different. The samples we have investigated for our project were, of course, here from the upper part, from different parts of this quartzitic sequence here. So I will show you some examples here. We identified different types of strata, and of course we imaged them with different techniques, so SEM and MicroCT imaging, of course. So this here is something that is a tight strata, which is directly out of this quartzitic lens that we have been. You can see here the mineralogy is really simple, 99.85 SeO2. This here are the residuals. You can make whatever you want out of it. You can argue that there is a pico% of clay in it, or this is just noise of your method. Yeah, so you can say this is a highly pure rock. And as you can see, we have a quite nicely distributed grain size distribution. This is one really nice thing about the Fontainebleau Sandstone. In average, it's about 250 microns diameter here and nothing else. But you can also see the pore system quite well. And if you go to the 3D image, it gets even a little bit better, because you can see here the pore bodies in between of the crystals. And that's more or less it. So the pore bodies are really lacking of connections between each other. Yeah. And that's something that, of course, you're not able to detect if you're measuring your permeability or anything else. Of course you can measure permeability, but you don't know how the flow paths are and the flow patterns are in your system. So that's why you can make this imaging quite nice. You can see some small, yeah, they're not really cracks. These are the planes between the crystals that are opening here at this point, but that's it. Then we have something that we call the porous strata. You can clearly see just qualitatively the pore system is a lot bigger, but still between the pore bodies, more or less, no interconnections here at this point. A second specialty that you can see, especially here in the ESEM image, is that you have a secondary quartz overgrowth upon your mineral face. And we will need to remember this secondary quartz overgrowth in a couple of minutes. And then we have the so-called intermediate strata in the close vicinity of this quartzitic lens. Mineralogy is still very easy. You can see here highly pure sandstone, but here something different happens. You see these pore bodies, and you can see these nice connections between the pores at the grain boundaries here. Yeah? So this is the intermediate strata, intermediate in terms of porosity permeability relationship. As I said, porosity, and this here are the blocks and the permeability for these blocks we have investigated. Yeah, so you can clearly distinguish between the different formation, and the three ones I want to show is the mark one here. The entire formation covers a wide range of porosity and permeability values. This data set here, 4 orders of magnitude. In total, the entire formation will stretch roughly 9 orders of magnitude for permeability. So that's why it's also of very high interest for the research companies. And the blocks I'm going to show is here the tight strata, the intermediate strata, and the porous strata. So they line up quite nicely here on this pore-perm relationship. If you want to talk about flow and the pore system, you also need to estimate somehow the surface area that the material is going to cover. And then you have a problem for this highly pure systems. With classical BET measurements, you come to an end. BET is not able, with nitrogen absorption, to detect the surface area reliably, because the surface area is too small. Yeah, it's just pure quartz, nothing else. So you need to trick a little bit and use another adsorbent. In this case, we use krypton, which has a better absorption characteristics for the BET. And then we're able to detect the specific surface area. Here we transformed it related to the pore volume. And then we can also clearly distinguish between the different blocks that I've shown you. And this one here is the one with the secondary quartz overgrowth, the green bubbles here. Yeah? So quartz overgrowth means higher surface area. And click, you can distinguish between the other blocks in your system. Okay, so but how do we come to the electrical properties? So the method that we're using here is called spectral induced polarization. And now the only formula that is going to appear will happen. So what do? We use a device that sends an alternating current into our pore system or into our rock. And we measure the complex conductivity or complex resistivity of the material and the phase shift between the current and the voltage signal. Yeah? So the blue one here is the current signal. It can be a sinusoidal signal or a rectangular signal, anything else. And then after some time, some characteristic time with a phase shift phi, your voltage signal, your potential arrives. And you can measure this phase shift. And this phase shift is characteristic for the pore system and the surface area and the interfaces in your system. Yeah? So you can use this to characterize your pore system. We typically apply this over a frequency range from millihertz to 100 kilohertz, and this only works for low brine conductivities. So not for in situ conductivities with fully saturated brines. Typically, we have conductivities in range of 100 millisiemens per meter or below. Yeah. And this is the formula how it looks like, just to be aware of. So we have the conductivity as a function of the frequency here, and the conductivity you can think about as a complex quantity. So the first part, the real part of the conductivity, is more or less ohmic conduction, nothing else. That's the contribution from pure ohmic conduction at this point. The second part here with this imaginary part, or quadrature conductivity as it is called, this is the so-called term that controls the polarization of your material and that you're able to detect inside of it. So, of course, there are different models how the material is able to polarize, or what is polarizable in your material. These are the most commonly ones. You got membrane polarization, stern layer polarization, interface polarization, and then you got really down to an atomistic scale. We just want to focus here upon the first and second one. So a very commonly used model is the so-called membrane polarization. So you apply an electric field, and what then happens is that inside of your liquid, inside of your sample, your molecules start to move, and if they reach a very narrow pore, due to the surface charge of your material, this narrow pores might be blocked. And at the blocking of these pores, you got an accumulation of currents at this point that you're able to detect. The second one is more or less happening on the electrical double layer, so a scale below this one here. And what happens here is you got your negatively charged surface of your grain, and then you have the positively charged ions in your fluid that layer around your material phase. And by manipulating this area, by giving again the alternating current inside of it, you apply some shear stresses at the ions that are docked here at the mineral surface. Yeah? So you start moving the ions here at this electrical double layer, and you're able to detect this signal as well. So everything I'm going to show you is a combination of both of these mechanisms here that take place. Yeah, to measure this in a low frequency regime, just for completeness, we use a 4-electrode system. We built this ourselves in our institute. You can buy a lot of machines that are able to measure IP, but you will not find that many commercial sample holders or cells for doing this. That's a straightforward 4-electrode system, so nothing really special. So the results for the 3 blocks, we got here the resistivity, the real part of conductivity, the imaginary part of conductivity, and the phase shift. So, and just for completeness, just focus here upon the phase shift. We measured the signal for different brine conductivities, and this here is for the tight strata. So the thing that we're focusing on here is the location of the phase maxima, the maximum phase shift, so the frequency, and you can transform this frequency to a time. So that's the characteristic relaxation time of this material. And then from this you can calculate a bunch of parameters like formation factors, cementation exponents. I don't want to stress this a lot. The intermediate strata, you can clearly see, has a different phase signal and a different location at this point. So we are more or less 1.5 decades higher here on frequency than for the tight strata, almost 2 decades. And for the so-called porous strata with the secondary quartz overgrowth, we see something like this. And you can trust me, this is called in the IP community a so-called double peak behavior. Yeah, this is the first peak, which is similar to the tight strata we have observed. And this here is the location of the second peak, which is affiliated to the secondary quartz overgrowth. So here we have a method that is really case sensitive to the different surfaces and interfaces in our system, which we were not able to describe without the imaging procedures. Yeah? So, and by having this information in addition, we can now try to characterize the formation more in depth. The colors here, the color coding is measured at different brine conductivities. Yeah? So the strongest signal for this highly pure material you will have at very low brine conductivity, so 6 millisiemens per meter conductivity. Yeah? And then we go up to 50 or even 250 millisiemens per meter. You can see the signal then is almost lost. Yeah? That's just because as you add more and more ions to your fluid, they got more and more immobile. Yeah? So that's just the reason why the polarization mechanism collapses at one point. So what's then commonly done for completeness, you can then plot the quadrature conductivity against the specific surface area. And then you can say, okay, so some rock samples of the Fontainebleau Formation follow the trend that has been long observed in the community, others don't. And these samples that do not follow this behavior are the tight and the intermediate strata. Yeah? So you can also use this for some kind of enhanced formation characterization. And then we, of course, need to discuss, yeah, so what's going on here in this pore systems? What is the dominating electrical flow path or hydraulic flow path at this point? Yeah. Okay. Last but not least, so this is more or less one of the last pictures I want to show you. You can correlate this relaxation frequency or relaxation time, if you want to, with other parameters from petrophysics, like the dominant pore throat diameter that you're able to get from mercury injection experiments. Also very commonly done in the community. And it was a quite straightforward approach to try to take the phase maximum and correlate it with the dominant peak in your MIP or MICP experiments. And for a whole bunch of sandstones, you got this really nice correlation. It seems to work that the pore throat dominates the electrical relaxation mostly. But a lot of samples you can see don't behave like this. It gets even worse. The samples with the double peak behavior only show one dominant pore throat in the MIP experiment. They should have two. Yeah? So 2 phase peaks, but only 1 peak in the MIP experiment. So what's going on here? Yeah? This is a work of my colleague Sabine Kruschwitz from the BAM Institute in Berlin. And we did this analysis also for the Fontainebleau. And the weird thing is, okay, we're still in the same formation, but the same formation, and this is the information I want to show you, you can find any type of this relaxation behaviors and of this relaxation patterns. You got the straightforward one, which behave as they should, and then you have this double peaks or even the ones that do not behave at all. So there needs to be a structure beyond the resolution limit that we're able to detect at this point that controls these mechanisms here. Yeah? So, of course, if you would like to investigate them, then we're at the beamline. Yeah? Synchrotron beamline, sub-micron resolution. That's where we need to go at this point. Okay, so to sum this up, the Fontainebleau itself is more challenging than it seems on the first step. It has a really easy mineralogy, but it has pore scale structures that are really complex, and you will not able to catch them without having an image impression of your pore system that you are going to investigate. Besides, some special or classical core analysis will not work in this material anymore, so you need to figure out something else. And if you compare this with MICP, you also can make a question mark if the MICP experiments are correct or not. By measuring the complex electrical properties, we can say, okay, we're able to clearly distinguish the different strata that we are going to investigate. So this method is really case sensitive to the systems that dominate all of the other petrophysical stuff here. And we also have a strong dependence on the specific surface area, which we are only able to measure with high efforts. And from this, we can calculate a whole bunch of other parameters. So I hope I've shown you how nice the imaging might work if you know what you're doing and how you can combine this with classical petrophysical analysis. Of course, the next step could be to use these geometries to make simulations upon these geometries on different scales to perform the upscaling and go to the reservoir model. So that's the final goal, what this all is about. And I can tell you it will keep us busy for the next 20 years. So if you're not finished yet, don't worry, you have a lot more work to do in this field. So thank you very much, and it is open for discussion.